Hello guys. Good morning to all of you. Today in this session, we'll be discussing specific heat. Okay, so am I live? Just confirm if everything is all right. Okay, I think there is some issue in the audio. Okay, can you hear me now? Okay, can you hear me now? I think everything is all right. एक बार बता दो सब लोग आप लोगों को. Good morning, Harry. Now is everything okay? Audio, video. Can you start? Okay. So specific heat. This is one of the most important topic from condensed matter physics, and you may get some question in the 5 mark section sometimes, and especially in GATE exam questions come from this specific heat. Many questions come. Okay, the specific heat of solid. One thing I would like to tell you, today is 27th of January 2025. You will be having your exam very soon, so focus more on solving problems, and now it is the time to give the full length mock test. Whatever preparation you have done, you just need to revise it. Okay, no new thing. Okay, if you have done it, you just revise them and practice questions. You do not need to cover the whole syllabus to attempt all the questions. Okay, you need to attempt minimum maybe from part A to 10 to 12 questions, from part B maybe again 10 to 13 questions, and part C around 10 to 12 questions. So if you can target that, and you will be having multiple options. Out of 25 questions, you need to solve correctly 10 to 13 questions, and out of 30 questions in part C, you need to solve around 10 to 12 questions. So that is not a big deal. So if we have done sufficient amount of syllabus, so you need to revise it and practice a lot of problems based on the topic, then you are good to go. Okay, so the main aim is minimum resources and maximum revision. Whatever you have done, of the question, it should not be like that. If you have covered that area and question comes, you have to make sure that focused on giving tests more and more, especially the full length test. And while giving the full length test, your concept will also be revised in the process. Okay, look, the specific heat of solid. The specific heat is the amount of heat energy required to raise the temperature of a mole of a solid by 1 degree. Okay, the specific heat, you can imagine it in this way. It is like heat capacity or a net mass. Heat capacity divided by mass. If you divide the heat capacity by mass, you get the specific heat capacity. So you see, specific heat capacity is denoted by C, and heat capacity is denoted by MC. Remember this one. Sometimes in the question, specific heat capacity is given, or sometimes it is given heat capacity. When heat is supplied to a solid, its temperature increases due to an increase in its internal energy. This internal energy rise can be attributed to two primary factors. Firstly, the increased vibration of atoms around the equilibrium position. that you can understand. Lattice, this will give rise to lattice specific heat. Another hello. Not audible 30-second. Not audible 30-second. Okay, now I think everything is fine. Okay. Let me know when you face that. I don't know why. I have done nothing. Specific heat is often measured at constant volume. You know, in case of gas, when you talk about gas, we'll have two specific heats, Cp as well as Cv. But when you talk about solid, we only have Cv. Because you see, in case of gas, if you give the heat at constant pressure or at constant volume, so it has great significance. The gas can expand easily. But for solid, it is rigid. Okay, either you do it at constant volume or constant pressure. So it is the same thing, right? It will not expand like the gas. So that is why one specific heat is enough for solid, but you require two specific heats for gas. Okay. So generally, for solid, we represent it by Cv. Cv is equals to dE by dt at constant volume. So we have already defined it in thermodynamics. Is the internal energy, T is the temperature of the system. Now in the specific heat, what is our primary goal? Our primary goal is to calculate specific heat of solid by using different models. Firstly, we'll talk about the classical theory. So as per the classical theory, what is the specific heat of the solid? Now it will show some discrepancies. Those discrepancies will be tried to be rectified by Einstein first. Then Einstein will give a reasonable description. The specific heat, the actual specific heat will match at high temperature, but the low temperature specific heat will not be explained by Einstein specific heat theory. So to tackle that, we have to shift to Debye theory, and Debye theory accurately almost represent the experimental specific theory, experimental specific heat variation. Okay, so this is the overall thing in this chapter. So firstly, let us try to understand this classical theory. So a crystal consists of atoms which are arranged in a periodic manner and bound together by strong binding force, that you know. In the classical theory, it is assumed that each atom of the crystal acts as three-dimensional harmonic oscillator. Harmonic oscillator is a quantum mechanical concept. For the time being, you know that in one dimension, this is the potential half kx square. Then you put this value to the Schrodinger equation and you get the energy eigenvalue En in one dimension, n plus half h cut omega. Okay, so this is in one dimension. If you consider two dimension, so such term will come again. Okay, so nx plus half h cut omega for x axis, ny plus half h cut omega will be for y axis, and nz plus half h cut omega that will be for z axis. So if you consider for 3D your energy expression, if you consider isotropic harmonic oscillator, you get n plus half 3 by 2 h cut omega, and this n contains both nx, ny as well as nz. Okay. So this is a 3-dimensional harmonic oscillator, and all the atoms vibrate independent of one another. So further, a system of n vibrating atoms or n independent 3-dimensional harmonic oscillator is equivalent to 3n identical and independent 1D harmonic oscillator. Try to understand this. If you consider n number of 3D harmonic oscillator. So this is equivalent to Tn number of 1D harmonic oscillator. No issue in this. So n number of independent 3D harmonic oscillator is equivalent to 3n number of one-dimensional harmonic oscillator. So assuming the distribution of oscillators in energy obeys the Maxwell-Boltzmann distribution law, the average energy of each harmonic oscillator is given. So what it is actually saying? Let's say we have the lattice, and at the lattice we have lattice points. So at the lattice point the atoms are sitting. Okay, atoms are sitting like this. So these atoms, I'm just showing one part of it. The atoms will vibrate about their equilibrium position. So this dotted line, let's say the equilibrium position. So the atoms will vibrate about this if you give some heat or some external energy. Okay. Now in the classical theory, it is assumed that these atoms is like the harmonic oscillator. They are vibrating, okay, about their mean position. So they are treated like 3D harmonic oscillator. 3D harmonic oscillator. Now let's say there are such n number of atoms. N number atoms each 3D harmonic oscillator. So you can consider that there are 3n number of one-dimensional harmonic oscillator. So as per the equipartition theory, average kinetic energy is given by half kT. From Hooke's law also, average kinetic energy, average potential energy is equals to half kT. So the total energy, okay, sum of kinetic energy and potential energy, you can see half kT plus half kT, so kT. Thus the total vibration energy of the crystal of n identical atoms or 3n one-dimensional harmonic oscillator is 3n per harmonic oscillator is average of E. Okay, so this total energy becomes 3n kT. If the total energy becomes 3n kT, so the specific heat Cv is equals to del E by del T. So this T will be gone. We will be having 3 NkB. NkB is equals to R. Okay. You know the formula. Kb Boltzmann constant is equals to universal gas constant divided by the Avogadro's number. Kb is equals to R by Na. So R is equals to Kb into Na. So we can write it 3R. So this result shows that the molar specific heat N is equals to Na for 1 mole. Molar 1 mole contains Na number of. So the molar specific heat of all the solid is constant. 3R. R is a constant, so this value is a constant and independent of the temperature. There is no mentioning of temperature and frequency. This is called Dulong-Petit law. Dulong's and Petit law. Dulong's and Petit's law. So some experimental element has been shown. You can see from here, you can see the discrepancy. Cv, this is the variation of the specific heat with temperature. So here it is, let's say 0 Kelvin. So these regions are low temperature region, and as you go along this axis, you are going or shifting towards the high temperature region, right? So you see from this you are going for, let's say for silicon, the specific heat capacity is varying like this, and it is reaching to the value of 3R, which is there. For silver, it is following some other path. The variation is different at the low temperature, but at the high temperature, it is also making it to 3R. So you see, at high temperature, this classical model is successful in explaining the specific heat, but at the low temperature, the specific heat is not matching. It should be 3R throughout. It should give you a constant curve like this, but for silicon you can see it is going like this. For silver it is going like this. So it is not following the specific heat, experimental specific heat at the low temperature. So this is a discrepancy. This needs to be addressed. How? N is equals to 3N. So it is like, you can imagine, one 3D thing. Okay, if you have, let's say, one 3-dimensional thing, so you can consider it like sum of 3 one-dimensional thing. It is equivalent to, so for each atom it is considered to be a 3D harmonic oscillator, right? Now one 3D harmonic oscillator is a combination of 3 one-dimensional harmonic oscillators. So you can say it is, if there are n number of atoms, you can say that there are n 3D harmonic oscillator, and each 3D harmonic oscillator is equivalent to 3 1D harmonic oscillator. So 3 into n, 3n 1D harmonic oscillator. Got it, Mulli? You can see here 3, here 1. Understood? Let's move on. So this discrepancy was tried to get fixed by Einstein, and Einstein gave his theory of specific heat. So what Einstein assumed, Einstein in 1911 attempted to resolve the discrepancies of the classical theory of the specific heat by applying Planck's quantum theory. According to Planck's quantum theory, the energy is quantized. Okay. Einstein retained all the assumptions of the classical theory as such, except replacing the classical harmonic oscillator by quantum harmonic oscillator. In the classical theory, you know, the harmonic oscillator which was used was classical. Okay. So these things, you know, this is for classical. So in classical theory, the harmonic oscillator was considered to be classical harmonic oscillator. For classical harmonic oscillator, you know the energy, right? Like in class 10, you read about the simple pendulum, and there you see the energy. What was the energy? Half m omega square x square, if I remember correctly. So the energy was like that. So that was continuous. But for quantum mechanics, the energy is quantized. It depends on the value of n. So Einstein did that change, that modification, that he used Planck's quantum theory, and as considered earlier, that each atom behaves like a 3-dimensional harmonic oscillator. Einstein just considered that these harmonic oscillators are quantum in nature. Quantum harmonic oscillator. This is the change he did. Then he took the energy En is equals to n plus half h cut omega or h nu. Omega is denoted by omega naught. Now some of the assumption you can see, in Einstein theory. Firstly, a crystal consists of atoms which may be regarded identical and independent harmonic oscillator. So this was also there in the classical theory. Okay, so he maintained this. Each atom is considered to be an identical and independent harmonic oscillator. A solid consisting of n atoms is equivalent to 3n one-dimensional harmonic oscillator. So he also maintained this. This was also considered in the classical theory. Thirdly, all the oscillators vibrate with the same natural frequency due to the identical environment of each. Same natural frequency omega naught. Later we will see that this was the reason, this third one was the reason that Einstein theory will also show some discrepancy, and that will be later removed by Debye theory. Okay, so as per Einstein, like each, there are the lattice atoms, you can say, so they are vibrating about their mean position, their equilibrium position. So as per Einstein, they vibrate with some natural frequency which is same for all the atoms. Okay? Same for all that omega naught. So he assumed this. And fourth, the oscillators are quantum oscillators. This is the main difference from the classical theory, that he assumed it quantum oscillator and have discrete energy. Previously it was considered to be having continuous energy. Fifth, any number of oscillators may be present in the same quantum state. This one also may later on will be proved wrong, but Einstein assumed this. Any number of oscillators may be present in the same state. It means he considered them to be boson, okay, not fermions. He considered that the state will be followed according to the Bose-Einstein statistics, not by Fermi-Dirac. The atomic oscillators form an assembly of systems which are distinguishable or identifiable, that is okay, due to the location at separate and distinct lattice state, and hence over the Maxwell-Boltzmann distribution of energy. Okay. Now let's say we are calculating the average energy of such oscillator. Oscillator means you can imagine the atoms here, okay, because atoms are oscillating. So if you want to calculate the average energy, so to calculate the average energy of an oscillator, we have already done it in thermodynamics. We have calculated the average energy of a quantum harmonic oscillator. Do you remember that? In the canonical ensemble, I think we have considered. What is En here? En is equals to n plus half h cut omega naught, and beta, you know it already. What is beta? Beta is equals to 1 upon kt, right? So if you remember, we got this result, half h cut omega naught plus h cut omega naught divided by e to the power beta into h cut omega naught, or h cut omega naught by kt minus 1. So we got this average energy. We have also done this derivation. You can expand it, you can put the values of n and you will get infinite series, and you will get this one. So what will be the expression of the internal energy of the crystal? From this, what will be the expression of the internal energy of the crystal? The expression for the internal energy of the crystal, This is the average energy. So total internal energy, you know, there are n number of 3D harmonic oscillator, each with, okay, this average energy is for one dimensional. So we have 3n dimensional, 3n one dimensional harmonic oscillators. We have to multiply with 3n into average energy for one dimensional harmonic oscillator, because we have considered, you can see, n plus half h cut omega. This is for one dimensional harmonic oscillator, so that is why we are writing 3n e. Okay, so this is equals to 3 by 2 h cut omega naught plus 3n h cut omega naught divided by e to the power beta h cut omega naught minus. Clear? So Cv will become d by dt, specific heat. Therefore the specific heat Cv, we know the formula, dE upon dt, dE upon dt. Look, this T is in Kelvin, not small t. Small t is in degree centigrade. This capital T is in Kelvin. So dE by dt at constant volume. This condition is special. You must mention this condition. For solid it doesn't matter, but for gas it matters. dE by dt at constant V. So you have to take derivative of this. Now this is the first term is a constant term, so that term is not contributing. For the second term, dE by dt, so it will be better if you consider beta to be 1 by kt, h cut omega naught by kt. So you have to take derivative. So this will give you 3n kb times h cut omega naught by kt whole square e to the power h cut omega naught by kt divided by e to the power h cut omega naught by kt minus 1 square. Okay, so let's write another line here, 3 by 2 h cut omega naught plus 3 in h cut omega naught divided by e to the power h cut omega naught by kt minus 1. So if you take derivative with respect to t of this expression, you get this one. So e to the power h cut omega naught by kt minus 1. So derivative of 1 by x is minus 1 by x square. Okay. So that is why square term is come. Now we have to multiply on the numerator derivative of this part, e to the power h cut omega naught by kt minus 1. So 1 is not producing anything. So derivative of e to the power h cut omega naught by kb. So derivative of e to the power h cut omega naught by kb is this same thing. Later you have to take derivative with respect to t of this part, h cut omega naught by kt. So h cut omega naught by kb into minus 1 by t square, derivative of 1 by t minus 1 by t square. So minus from this and 1 minus initially, minus plus. Okay, then we could write this h cut omega naught already there. From the derivative h cut omega naught is coming, so h cut omega naught square. kb was once here, but we have taken twice, so that is why kb is multiplied. Okay, and t square is coming from the derivative. So simple derivative. Okay, so you can see how the specific heat is varying. So now Einstein defined Einstein temperature. So let the Einstein temperature theta E for Einstein, E for elephant, E for Einstein, h cut omega naught by kb. Okay, theta Einstein. So you can see this is Einstein temperature, h cut omega naught by kb. So under this modification, under this nomenclature, what will be the value of CB? This will be 3n kb theta e upon t whole square e to the power h cut omega naught by kb. So theta e by t divided by e to the power theta e by t minus 1 whole square. Okay, so this is the actual form of specific heat as per Einstein model. Now it is the test time. So we'll test at different temperature range, two temperature broadly, at low temperature and at high temperature. Okay. So this is the Einstein's expression for, this is the expression for specific heat as per Einstein's theory. So few important feature you should be keeping in mind, that it has theta e by t, 1 by t square dependency here, and it is exponentially increasing, exponential theta e by t. Okay, so remember this one, exponential factors are all coming. So we'll be considering two cases to verify this Einstein theory, how much it is relatable to the real life scenario. So case 1, high temperature. So at high temperatures, what we will have? Theta e. Okay, theta e okay, h cut omega naught by kt. So if temperature is high, what does it mean? Kt is high, means Kt is much greater than h cut omega. So we can say that T is much greater than h cut omega naught by kb. It is theta e, no? So T is much greater than theta e. If T is much greater than theta e, we can calculate that e to the power theta e by t minus 1. So theta e by t much less than 1. Background noise. Hope it gets resolved. It is better now, Harry? It is better now. I think it is better. Okay, let me know whenever you see this. Actually, you're seeing I'm not doing anything, but it is automatically, I don't know why. So it is over theta e by t minus 1. So theta e by t is much less than 1. So if you have, let's say, something which is very small, x is very small, so we can write 1 plus x, right? So we can write approximately it is 1 plus theta e by t, but theta e by t is very small. So we are getting theta e by t, that is equals to h cut omega naught by kT, and hence CV becomes 3n kb h cut omega naught by kT whole square e to the power theta e by t is equals to 1 plus theta e by t. So 1 plus h cut omega naught by kT divided by e to the power theta e by t minus 1. So there is h cut omega naught by kT whole square. Now you see, since h cut omega naught by kT tends to 0 for large t, if we make t infinity, 1 by infinity is 0, so this is tending to 0 for large t. And you see, this thing and this thing get cancelled. So CV becomes approximately this thing get cancelled, 1 and this h cut omega naught by kT, this term is negligible. So we will have 3n kb, that is 3r. So it is exactly matches with the classical theory, which is exactly matching with the Dulong's and Petit's law. Based on classical theory. So for high temperature we have seen. Now let's scan this for low temperatures. So the second thing which we will be doing, we will check this behavior at the low temperature. At low temperatures, kT, T value is low, so it will be much less than h cut omega naught, right? So T is much less than h cut omega naught by kb. That means T much less than theta e. So when it is there like this, so h cut omega naught by kb, here also we can write h cut omega naught by kT is much greater than 1. If something is much greater than 1, if minus 1 is there, so this minus 1 can be neglected, right? Because this is a very large number. We can write it e to the power h cut omega naught on kT. So if you consider this expression, so e to the power theta e by t is much greater than 1. So this thing is superior as compared to 1. So 1 is negligible. E to the power theta e by t whole square, and this e to the power theta e by t. So 1 e to the power theta e by t will get cancelled. So what will you have? Cv is equals to 3n kb theta e by t whole square and 1 upon e to the power theta e by t. This is approximate. So this is equals to 3n kb theta e by t whole square e to the power minus theta e by t. So it is exponentially varying. So for t much less than theta e, the heat capacity is proportional to, look, whenever you have, you see here there is a dependency of 1 by t square as well. But when there are exponential terms in an expression, then exponential terms always dominate. So that is why the heat capacity is proportional to e to the power minus theta E by T, or e to the power, or is a misnomer, you can use, that is e to the power minus h cut omega naught by which is the dominating factor. But experimentally it is not found like that. But experimentally most of the solid, what does it show? Experimentally it is found to vary as T cube for most of the solids. Understood? Understood? So we can sadly comment that thus Einstein's theory failed to explain the actual variation of specific field. So if we take Einstein's model, okay, actually if I consider variation of Cv and T environment, will be like this. This is theoretical. So this is not matching with the experimental one. Or you can just remove this. Okay, we'll draw the curve again for d by 3. For the timing, do not follow. Now this discrepancies was removed by d by theory. D by theory of specific heat. This is the ultimate one which explain the specific heat. In this model, vibrational motion of the crystal as a whole was considered to be equivalent to the vibration motion of the system of complete coupled harmonic oscillator, which can propagate a range of frequency rather than a single frequency. So in the Einstein theory, we have seen that it is only having one frequency, natural frequency omega naught, considering the identical environment. But in actual scenario, it is not like that. Instead of a single frequency, it can vibrate in a range of frequency, which can propagate a range of frequency rather than a single frequency. Debye proposed that the crystal can propagate elastic waves of wavelengths ranging from low frequency of sound wave to high frequencies corresponding to the infrared absorption. So various frequencies can exist. This means that a crystal can be a number of modes of, for a crystal. Okay, I should have modified this grammar. Actually, grammar is very poor here. Okay, let me fix it. This means that a crystal can have a large number of modes of vibration. Okay, number of vibration modes per unit frequency range is called the density of mode Z nu. So you can imagine that there are some frequency range of d nu. So how many number of different vibrational modes exist? Let's say it is nu plus d nu. So the interval is d nu. How many number of vibration modes are there? That is denoted by Z nu. Okay, Z nu, d nu. So in general, the elastic waves propagating in solids are of two types. Okay, two types of elastic waves we see inside solids. Number one, the transverse waves. And number two, the longitudinal waves. So both will have different vibration modes, and that is why if you write the density of modes, okay, density of modes, number of modes in the interval of frequency between nu and nu plus d nu. So Z nu, d nu. This is written as 4 pi v into 2 by Vt cube. Vt is the velocity of the transverse wave, plus 1 upon Vl cube times nu square d nu. Okay. So you can imagine it in this way. We have Z nu, the density of modes, versus the frequency. Frequency is starting from 0. So it can change like this. So ultimately it will be having some frequency nu d. That is called the d by frequency. If you want to calculate the total number of modes, or the total number of modes, or the total number of modes, what you can do? Total number of vibrational modes, or the total number of vibrational modes with frequencies ranging from, you can see 0 to the maximum d by frequency nu e, each integration of Z nu d nu 0 to nu t. So can you tell me what it should be equal to? If you consider there are a number of atoms, what it should be equal to? Total number of vibrational modes. You know, each atom will be vibrating in different modes. N number of atoms, n number of three-dimensional quantum harmonic oscillator. So 3n number of one-dimensional quantum harmonic oscillator. So if you calculate this, all the vibrational mode, it should be equals to 3n, right? So that is why we can write it 0 to nu d, n or 3n, because although 3n, although it is n 3-dimension harmonic oscillator, but they are treated like 1-dimensional harmonic oscillator. Combination of one 3D harmonic oscillator is a combination of 3 1-dimensional harmonic oscillator. That is why this 3n is coming. Okay, otherwise n would have come. For 4 pi v, 2 by Vt cube plus 1 upon Vl cube nu square d nu is equals to 3n. So this is equals to 4 pi v 2 by Vt cube 1 by Vl cube nu square d nu is nu cube by 3. And if you put the limit, nu is nu d, so nu d cube by 3, this is equals to 3n. So this total energy E, you can imagine that average energy times this, we have associated average energy per mode. What is the average? Planck's theory we have already calculated. On Planck's theory, what is the average energy of a 1D harmonic oscillator? Average energy H nu by kT minus 1, average energy. Okay, now the sound is back. Okay, it back with noise. I think noise is now increased. Okay, let me. Now the noise is gone. Oh, you can see there is too much of technical things. Now the noise is gone, but the sound is also gone. Hope it gets better. Hope it gets better. Now I think we can continue. Hope it gets better. It's like frequency adjusting ready. Yes. Now I think we can continue. Likewise. You have to be expert in various things. Okay. Otherwise, life is very unpredictable. You can see everything I have kept proper. It's just like I am removing the plug, inserting it. It is getting fixed. Oh. Anyways, let's continue. E average is this from Planck's theory h mu by d to the h mu by kt minus 1. So we'll put that value. So this is equals to 0 to mu d, z nu d nu. So this is the value 4 pi. Look, h nu is there. So h d 2 by vt cube plus 1 by vl cube integration 0 to mu d. Look, this nu and this nu cube. Okay, so we have nu cube d nu divided by e to the power h nu by kt minus 1 to the power. Okay, this actually we have put this expression, 4 pi v 2 by vt q 1 by vl cube nu square d nu. So nu square d nu and this nu, that is where nu cube. I hope this is clear to everyone. Now you know the value of 4 pi v into this whole thing is 9n by nu d cube, right? So this becomes 9 n h by nu d cube 0 to nu d nu cube d nu by e to the power h nu by kt minus 1. Why you could write? Because 4 pi v times 2 by vt cube plus 1 by vl cube is equals to 9 n by nu d cube. Now if you put, let's say, h nu by kt equals to x, h nu d by kt is equals to xm, let's say. So what will be the value of nu? Nu is equals to kt by h times x d nu kt by h times dx. So here E becomes 9 nh by nu d cube kt by h to the power 4 0 to xm by changing the limits. So it will become x cube dx divided by e to the power x minus 1. Now this nu d can be taken inside, so it will become a 9 n KT by h nu d cube, it will become cube, okay, 0 to xm x cube dx by e to the power x minus 1. So this is the actual expression of the Debye theory. Now let's say the Debye temperature. Let's consider the Debye temperature. The way we consider Einstein temperature, here we have to consider Debye temperature. Debye temperature is theta d, that is h nu d by kb. Okay, theta d is equals to h nu d by kb. So xm will be, see, h nu d by kt was there, so theta d by t, and that is why your E value will become 9 n kt t by theta d whole cube 0 to theta d by t x cube dx divided by e to the power x minus 1. So this is for 3 dimension, right? So if you consider different cases for different dimension, we can write a more general expression. E is equals to 9 n d is the dimension kt t by theta d 0 to theta d by t x to the power d dx for x minus 1. For one dimension, d is equals to 1. For two dimensional case, d is equals to 2. For 3D, d is equals to 3. So if you consider, so this will not be 9, this will be 3. 3n dkt, so d equals to 3 we put, so 9n kt t by theta d cube 0 to theta d by t x cube dx by e to the power x minus 1. You will get got it. आज बहुत डिस्टर्बेंस आ रहा है ना आज. Let us consider the different cases now. Okay. Case 1, let's say for high temperature. High temperature, what should you expect? We expect it should give you 3R. So for high temperatures, Kt is much greater than H cut omega. Okay. Or better we write H nu. D, let's say. So T is much greater than theta D. Okay. So E, we are considering 3D cases only now for the time being. Consider 3D case. So we had E is equals to 9 NKT T by theta D Q 0 to theta D by T x cube dx by e to the power x minus 1. Now what is x? X is equals to theta D by T. Theta D by T much less than 1. That means x much less than 1. If x much less than 1, e to the power x minus 1, approximately 1 plus x minus 1, that is x. Can I write it in this way? E to the power x minus 1 is equals to x. Can I write it in this way? Let's record it down. Little more time this system is not able to handle. More time this. Okay, at least the noise will not come now. Audio quality is a little bit degraded, but so this much you have got. E to the power x minus 1 is approximately x. So this becomes x square dx. You put this in 9 by x cube dx x square x cube by 3, so 3, and this will get cancelled. Give you 3 nkt. 3 nkt. How is the sound now, Hari? PV is equals to E by dt at constant V. This is 3 nkb. This is what we expect. We have 3R. So we can conclude thus at high temperatures dy theory also obeys the Dulong's and Pitt. As obeyed by the classical theory and the Einstein's theory. It's like sound come from far, but now noise reduced. Yes, yes, yes. Adjust little bit. Actually, the microphone is creating that noise. It is changing its state. Okay, flip flop बन गया है ये. Now at least that non-uniformity will not be. You will get some sound to hear. Okay, we are almost at the end of the lecture, but let's talk about the second case. Okay, at low temperature. At low temperature, the real crystal, real solid gives you T cube dependency. At low temperature, whether you are getting it or not, T will be much less than theta D. Okay, xm, which is theta D by T, and now theta D by T is much greater than 1, so it is approximately reached to infinity, and as a result of that, E will become 9 nkbt, 9 nkb. पता नहीं क्यों एक 9 nkt, 9 nkt into T by theta D cube 0 to infinity x cube dx by e to the power x minus 1. This was the original expression. Now if you put this thing, it will be okay, little bit theoretical. It is 9 nkt into T by theta D whole cube. This will come out to be pi to the power 4 by 15. Okay, look, previously we were not able to do this integration because theta d by t was there. We did it, but now theta d by t, that in upper integration limit, it becomes infinity. So this integral, you need to remember that 0 to infinity x cube dx divided by e to the power x minus, it has a value of pi to the power 4 by 15. So the general formula is pi to the power n plus 1 divided by 1 into 3 into 5 into 2n minus. So put n equals to 3. So pi to the power 4 divided by 1 into 3 into 2 into 3 minus 1. So 3 into 5. So this is equals to how much? Three by 5 n kb e to the power 4 by theta d cube and pi to the power 4. क्या पूछ रहे हो? xm tends to infinity for limit. Yes, the limit was what? The limit was 0 to theta d by t. So theta d by t you have taken x, right? 0 to xm. Here for low temperature t is much less than theta d, so theta d by t tends to infinity. xm is infinity, so that is why the limit is infinity. Okay, so once you get E, we can easily calculate CV. CV is equals to dE by dt or del E by del T, constant B. So this will give you 4t cube. Okay, so 12 by 5 pi to the power 4 n kb E by theta d whole cube. The main thing is here the t cube dependency. So we are getting the t cube dependency. Or this is equals to 12 by 5 pi to the power 4 n kb is r by 30. Here also any of the expression you can use. So ultimately we can say that CV is proportional to t cube. This is what is expected or obtained from the experimental result. This is the behavior at low temperature. This is called d by t cube law. Let us solve some problem now. Here atoms considered as gas. No, atoms considered as harmonic oscillator, quantum harmonic oscillator. So in solid, atoms cannot move independently. Okay, it remains fixed at some location and it vibrate. Okay? So this vibration is considered to be following the harmonic oscillator. It is considered to be a three-dimensional quantum harmonic oscillator. Which is equals to 3 one-dimensional quantum harmonic oscillator. So when you, let's say, there are thousands, there are numerous number of such atoms inside, and that makes a solid. That makes a, now whenever you give heat or energy, what will happen? This heat and energy will increase the vibration. If you are at low temperature, if you consider, this vibration will be low. At high temperature, the vibration will be high. And EV is the rate of change of energy. How much energy is changed per unit change of temperature. This is what it is. The variation of the specific heat C of a crystalline solid can be obtained using Dulong-Petit's law, Einstein model, and DModel. So this is a summary. You can say this problem is a summary. So for Dulong-Petit law, it is a constant. Okay. For Dulong-Petit law, it is a CV is equals to constant. It is asking you for low temperature. ये कैसे होगा? Dulong-Petit's law at low temperature or at high temperature, it is constant throughout. Now for Dulong-Petit's, Einstein e to the power minus a by t Look, for high temperature, this also gives you 3R, this also gives you 3R, this also gives you at high temperature. So at high temperature, all of them are constant. For low temperature, Coulomb-Petit's law gives constant, Einstein theory gives 1 by t square exponential minus a by t. A will exponent d by t cube. So from this d by t cube we can easily select. Look at this problem. The d by temperature of carbon diamonds is 1850 Kelvin. Calculate the specific heat per kilomole for diamond at 1220 Kelvin. The CV expression you have already got. What is CV? CV is equals to 12 by 5 pi to the power 4r T by theta dq. Here you can use this relation mainly. Calculate 12 by 5 pi to the power 4r T by theta dq. Okay. CV 12 by 5 pi to the power 4r T by theta dq. Okay. D by temperature means theta d is given. Temperature T is given. So if we calculate this 12 by 5 pi to the power 4, this will give you approximately R by 1850 approximately 0.45 10 to the power 2.45 joule per kilomole per kilo. This K is kilo, okay, and this capital K is Kelvin. In this problem, internal energy versus T graph for Debye model. Internal energy versus T. So CV we got it T cube, right? Internal energy, how do you get CV? By taking derivative of U with respect to T, we get CV. If it is T cube, U must be having the dependency of T to the power. Only after taking derivative becomes T. So T to the power 4 dependency, how it looks? It looks like it is not constant, not linear. It is not function like this. They are not. This is the discontinuous. Okay. R is equals to NK. You need R is equals to the universal gas constant. Na? Universal gas constant, you know the value. 8 point something was there, 314. K is equals to R by N. Okay, R is equals to NK, that also you can use. But you know the value of R, na? Universal gas constant. Look at low temperature, only the acoustic modes contribute noticeably to C. And the Debye model provides a good And with increasing temperature, optical modes start to become excited too, and CV curve changes gradually and takes the form of Einstein. So this acoustic mode and optical mode that we'll discuss in the next class while discussing the lattice vibration. Okay. For the time being, you know that at low temperature, Debye model gives a dependency, good description of the specific heat. For Einstein model, the higher temperature gives, at high temperature, Einstein model gives better description. Now, let me give you a very important formula, the specific heat capacity dependency on temperature on different dimensions. So you just remember this formula. CV proportional to T to the power D by S. T is the dimension, D is the dimension, S is the power of K or omega. Look, to know about S, omega is proportional to K to the power S, or E is proportional to K to the power S. Now S is equals to 1 for massless particle like photon is massless. Photon, you understand the quantum of light. Phonon is the quantum of sound, that inside the solid lattice, phonon is the equivalent to photon that we have in light. Photon and phonon. And look, electron is massive, but electron on graphene sheet is considered to be massless, magnon. So in general, for electron you can take S is for massive particle like electron. So if nothing is mentioned, by default you can take S is equals to 2. So that is why we get E equals to h cut square K by 2, which is proportional to K square. So using that, if you consider one dimension, CV proportional to T, D is 3 by 1, because here phonon we have to consider. That is what you get in case of Debye theory. For 2D, this CV will be proportional to T square. Sometimes question may come on this. The dimension will be mentioned, and you may be asked to calculate the dependency of CV on T. CV proportional to. This variation is at low temperature. Remember, for high temperature it is 3R in 3D. Okay, now this question, the excitation of a three-dimensional solid are bosonic in nature. In their frequency, omega and K related by this, omega proportional to K square in the large wavelength. If the chemical potential is 0, the behavior of the specific heat of the system at low temperature is proportional. Look, what we are seeing 3 dimension. Instead of 1D, here it is 3D, D is equals to 3, K is equals S is equals to 2. So CV is proportional to e to the power D by S. Here for 3 by. Okay, option C. CV is proportional to T. Yes, one by one, that is why T. Look, do you know the value of 3R? What is the value of EV is equals to 3R? R is what? R is 8.314 at 8.3 joule per Kelvin per mole. So this is around approximately 25 joule per Kelvin per. Now you know some special lines you should write. D by temperature. The D by temperature indicates approximately the temperature below which quantum effect may. Be proportional to T for 3D. For 3D, you see T to the power 3 by 1. So that is a T cube now. Here S is equals to 1. We have written for S is equals to 1 because we are considering phonons. Phonons are massless. Oh, sorry. I understood. That is what we were talking about from this long. Sorry. One last thing, I mentioned about electronic specific heat. Right? So let's have some discussion on that. Electronic specific electron contribution in the specific. This is observed in case of metal. Okay, so C electronic. So contribution from the electrons is negligible. Most of the contribution comes from the atoms, but electron also contribute. That value is pi square Na AB square by twice EF times E per mole. Okay. So for solid we have seen T cube dependence at low temperature, but in case of metal it is different. It is important only for low temperatures in metals where it becomes larger than T cubed dependent phonon contribution. So specific heat in case of metal is sum of two terms AT plus BT. This is at low temperature. Normal solid we have only this term, second term T cube dependency, but for metal we have this AT as well. So the value of A is y square Na AB square by 2EF, value of A, and the value of B is 12 by 5, we know, that will be 4 Na AB divided by theta, where this theta d is equals to h nu d by one more formula I'm quickly giving. Oh. d by frequency nu d is equals to Vs times 3 Na by 4 pi p to the power 1 by 3 Vs Cna by 4 pi V is equals to m by rho to the power 1 by. ds is the velocity of sound. So d by frequency, so d by temperature in terms of this, therefore the d by temperature d is equals to h d h e s by Tb three Na rho 4 pi m to the power mass of 1 mole atoms. Rho is the density of the crystal. So you can try this problem at home. Simple, nothing is there. If not solved, you can let me know. How many energies are given? Temperatures are given, d by temperatures. Cv of x varies like this, Cv of y varies like this, then you have to find out the ratio. So you can do it. Chalo, bye bye. Take care, guys.